Tel Aviv University Computer Science School, and here we'll talk about analyzing optimization and generalization in deep learning via trajectories of gradient descent.
This is not the right. No, this is not the right slide. These are not my slides. Oh, okay. Okay, sorry about this. It's number 16. Okay. All right, so as Amir said, I will talk today about analyzing optimization generalization in deep learning through trajectories of gradient descent. So let's start by giving a little bit of context and the main argument that I'm trying to make in this talk. So in the context of deep learning, when we talk about optimization, we typically mean the process of fitting training data by minimizing some objective, some loss function. And generalization refers to controlling the gap between train and test error, for example, by adding regularization. And the behavior of optimization generalization in deep learning is very different from classical machine learning. Let's reflect about that. So in classical machine learning, typically we choose problems and models in a way that the training objective will be convex. That means that there's just typically one global minimum, and it's efficiently attainable. You could reach it efficiently using various algorithms. And essentially the choice that you make on which algorithm to use, that mainly affects the speed at which you converge. It doesn't affect the final solution that you will get to. The final solution is the global minimum. For generalization, there's the famous bias variance trade-off, which essentially means that if I add on regularization, then I decrease the gap between train and test error, which is a good thing. But on the other hand, the training error goes up, which is a bad thing. So there's a trade-off, and overall, I think it's safe to say that theoretical learning community had a feeling that we have a decent understanding of what's going on. In deep learning, the situation is very different. We allow the objective to be non-convex, and there's not just one global minimum, there are a lot of them. And a priori, it's not clear that any of them is efficiently attainable. Nonetheless, on typical problems, somehow variance of gradient descent usually reach one of these global minima. And in terms of generalization, the situation is even more peculiar, and that is that we know empirically that some global minima generalize well, and others don't. And for some reason, on the kind of problems that deep learning works on, which is a pretty wide array of problems, the solution that's found by gradient descent is often one that generalizes well. And maybe most surprisingly is the fact that there seems to not be a bias variance trade-off, not in the traditional sense at least. Huge models can generalize very well with no explicit regularization. The way we view this is as an implicit regularization that is induced by the optimizer. But we don't really understand this phenomenon well. Overall, these questions are not well understood in deep learning. And the argument that I will try and make today is that maybe the concepts and the tools that we've developed over the years for classical machine learning are just insufficient for understanding optimization generalization in deep learning. And maybe there's no way around carefully analyzing the process of learning, meaning the trajectories of gradient descent. Okay, so that's kind of the main position that I'm making, and I will try to make this case using deep linear neural networks. Okay, so this is the content of the talk, based on 3 papers, last year's ICML, this year's ICLR, and another one in NeurIPS next month. With my colleagues in Princeton, Sanjeev Arora and Elad Chazan, which is speaking later today, and students Yuping Luo, Wei Hu, and Noah Gulowich. Okay, so let's go. So what's a linear neural network? A linear neural network is a fully connected neural network with linear activation. Put differently, it's a linear mapping from input to output, but I don't parameterize this mapping directly as a matrix, I parameterize it as a product of matrices. Okay, so from an input-output perspective, representationally, these models are trivial. It's just linear. But from an optimization and generalization perspective, these models are highly non-trivial. They admit multiple global minima, and the kind of solution that you reach on underdetermined problems is something that could vary. And for this reason, these models are often viewed as a theoretical surrogate for nonlinear neural networks. and they are really studied extensively. This is just a small sample of papers from the recent couple of years. There are many more. What we're going to do is analyze the trajectories of gradient descent over linear neural networks, and then we're going to use the results to reason about optimization and generalization. So in terms of the trajectory, I'll just show you the final result. The question that we ask here is as follows. When I run gradient descent over a linear neural network over these n matrices, at every point in time, there is an effective end-to-end mapping. We call this the end-to-end matrix. That's just the product of the n matrices. And this thing moves somehow in space. And the question is, how does it move in space? What kind of dynamics does it follow? What kind of trajectories? It's not following gradient descent because we're not running gradient descent on a linear model. We're using a linear network and running gradient descent on that. What we show is that this end-to-end matrix follows these dynamics over here. We call this the end-to-end dynamics. If you ignore the blue term here, this is just gradient descent over the loss. Vec means to vectorize a matrix. It's meaningless if you don't have this blue term. This blue term is what folds in all of the effect of the linear neural network, and this is a preconditioner, a PSD matrix. We have a closed form expression for it. I'm not going to present it here. I'll just say that in some sense this preconditioner stretches the gradient more in the directions, the singular directions of the end-to-end matrix that have a large singular value. So if you've made significant distance in some direction, the gradient's going to be stretched more in that direction. Bottom line is that if we had a linear model and we over-parameterize with a linear network and run gradient descent on that, we implicitly induce a preconditioner that promotes movement in directions already taken. This is an important result, and it's going to facilitate all the results that I will show you on optimization and generalization. Let's go to optimization. The classic or prominent approach in deep learning for reasoning about optimization is, at least until recently, was to look at critical points in the objective. These are points where the gradient vanishes. Okay, so you could have a local minimum, could be bad, so the objective is much higher than the global minimum. It could be good, so the objective is close to the global minimum. You could have a saddle. It could be strict, so the Hessian has negative eigenvalues, or it could be fairly flat. The Hessian does not have eigenvalues, negative eigenvalues. And a result that was shown in different flavors in the last few years is the following. If my objective does not have any bad local minima, and it doesn't have any non-strict saddles, so all the saddles are strict, they look like this, then gradient descent will converge to global minimum. And so this is kind of appealing because we can prove convergence to global minimum just by looking at geometry of critical points. And indeed, many motivated by this result studied the validity of these two properties, no bad local minimum and non-strict saddle. However, this kind of approach hits a wall right at the outset when you try to apply it to a deep model, 3 or more layers. Because for a deep model, property 2 is false. All the second derivatives are going to be 0, and you will get a non-strict saddle. So this kind of approach doesn't really go through. What we do is apply our trajectory analysis, and I'll just show the result that we prove. Suppose you're optimizing the L2 loss, and you initialize the linear neural net such that 2 conditions are met at initialization. They are grayed out because I do not want you to try and parse this. Just treat it as 2 conditions. Under these 2 conditions, gradient descent is going to converge to the global minimum exponentially fast. It's called linear rate convergence. Okay, so we have a result proving convergence of gradient descent to global minimum, exponentially fast convergence under 2 assumptions on initialization. What can we say about these assumptions? Number 1, we know that in some sense they're both necessary. So if you drop one of them, the theorem is going to be false. It's easy to come up with counterexamples where convergence fails, or you could even diverge. So both of these conditions are in that sense necessary. We also know that if you have an output dimension of 1 and you use a random initialization that's not exactly what people usually use but close, both of the assumptions are going to be met with high probability, like probability 0.5. So with output dimension 1, use this random initialization, probability 0.5 or more, you will converge to global minimum exponentially fast. Overall, this is the most general guarantee that I'm aware of for gradient descent training a deep, that's 3 or more layer model, reaching global minimum in an efficient number of iterations with an efficient model size, something that you can imagine running on your computer. Okay? And this is thanks to the trajectory analysis. What we're going to see now is something that I think is more surprising, and that is the effective depth on optimization. Okay, the conventional wisdom is that convex optimization is easier than non-convex, and that means that training shallow models is easier than training deep models. And what we're going to see is that this is not always the case. Okay, so these are the end-to-end dynamics that we derived. Here's our preconditioner. What we prove is that for any p greater than 2, there exist settings with the loss being LP loss, that's convex. And in these settings, the end-to-end dynamics reach the global minimum much, much faster than gradient descent. So there exist settings where you have a convex loss and you can train a linear model, but if instead of that you train a linear network and in a non-convex problem, seemingly without giving you anything, it would lead to much faster convergence. Okay? So this is the theoretical result, and the question is how relevant are these settings to practice? For that, we've run experiments. We run quite a lot of them. I'll just show you the basic one. This is a regression problem from UCI machine learning repository, L4 loss, because we need p greater than 2. And this is what you get when you run a 1-layer model. That's in blue. That's a convex problem versus a 2 and a 3-layer model, which are non-convex problems. And you see the convergence is much, much faster with the latter. This is log space. That's how the loss decreases. So overall, depth can speed up gradient descent even without any gain in expressiveness and despite the fact that it leads to non-convexity. And you can't hope to reach this kind of conclusion by looking at critical points or anything like that. You have to look at the specific trajectories that are taken. Okay? All right, so let's now move to generalization. So the setting that we look at here is one where generalization carries a very concrete meaning, and that is matrix completion. Okay, in matrix completion, our job is to recover a low-rank matrix given some subset of entries. Okay, it has a lot of applications and recommender systems, things like that. For example, the Netflix prize. And formally, what we're trying to do is find a matrix that has minimal rank subject to it agreeing with the observations. That's our objective. And there's a convex programming approach to this, and that is to replace rank by nuclear norm. That's the sum of singular values. Instead of minimizing the rank subject to agreeing with the entries, you minimize the nuclear norm subject to agreeing with the observations. Okay? Somewhat surprisingly, I guess today it's well known, but at the time it was surprising, is that this approach will actually give you perfect reconstruction if you have enough observations. Okay? A deep learning approach to this problem would be the following. We call this deep matrix factorization. And basically what you do is you just parameterize the solution as a linear neural network, and you fit the observations with gradient descent. Okay, so I parameterize the solution as a product of n matrices, Wn, Wn minus 1 to W2, W1, and I run gradient descent on that. I am not necessarily constraining the ranks, the hidden dimensions, so basically in the basic settings, every matrix can be represented. I'm not constraining the rank in any way. Okay? So there's a previous work on this model only for depth 2. This is by Surya Gunasekar and Nati Srebro, which should be speaking, I think, right after me, and others as well. They analyzed the depth 2 case, and what they show there is a number of things. First of all, empirically, they show that oftentimes you get accurate recovery. You successfully recover a low-rank matrix, even though there's no explicit regularization. They give a conjecture that implicitly gradient descent solves that convex programming approach. It implicitly drives you towards a minimal nuclear norm solution. And they were able to prove this in a certain restricted case. Okay? So what we did is look at the deep setting, where you have an arbitrary number of layers. And the first thing we thought is maybe it's possible to capture the implicit regularization using some norm. Okay, these are the kind of things that we're used to from classical learning theory. So here's an experiment. This is what happens when you compare a linear neural net of depths 2 and 3 I'm showing here versus the minimal nuclear norm solution. On the left, that's the reconstruction error. On the right, that's the nuclear norm. So these two plots match. And the x-axis, that's the number of observations. So every tick here corresponds to a different experiment, and I vary the number of observations in the experiments. So you can see two things here, at least. Number one, you can see that the deep model in orange here provides much more accurate recovery than the shallow one. So depth enhances the implicit regularization towards low rank. The second thing that you see is that, at least here, it doesn't seem like the implicit regularization is nuclear norm minimization. You can see that when you have a lot of observations, then nuclear norm minimization gives you perfect recovery, and so do linear nets. So obviously everything coincides. But when you have a small number of observations, then minimal nuclear norm doesn't do a good job recovering. And the linear nets do a much better job, and they are willing to sacrifice having higher nuclear norm. So at least in this setting and in others we tried, it doesn't look like nuclear norm minimization is what's happening. To add to that, we actually proved that in the restricted case where Gunasekar et al. Proved that depth 2 minimizes nuclear norm, actually any depth does so as well. So it doesn't seem like there's something particularly special about depth 2 and nuclear norm. Whatever we know for depth 2, we know it for higher depths as well. This kind of led us to believe that maybe it's not even possible to capture the implicit regularization with just one norm. That's what we're used to from classical machine learning, but it doesn't mean that this is what's going on in deep learning. And then we again resort to our trajectory analysis. Okay, so this is the end-to-end dynamics that we derived. In green, that's the end-to-end matrix. Here's our preconditioner. And if you denote the singular values of the end-to-end matrix by sigma, sigma r, then we can show that sigma r moves proportionally to itself to the power of something, and that something gets bigger when you add more layers. And what this means is that when you start off, when you initialize, and all the weights are small, so the singular values are small, they barely move because of this coefficient. And then once one of them gets large enough, then it starts moving faster and faster because the coefficient increases. So it's kind of this like rich get richer phenomenon. And this actually leads to bigger gaps between singular values. And here you can see it empirically. This is the evolution of singular values during gradient descent on a linear neural net. Depth 1, depth 2, depth 3. So with depth 1, you can see that all the singular values rise together. There's no attenuation of movement for small singular values and no enhancement of movement for large singular values. With depth 2, you can see that the effect starts kicking in. When the singular values are small, they barely move, and then some of them, once they get large enough, they start moving rapidly, and the others are left behind. So you get a small number of large singular values, and all the rest are smaller. So there's a bigger gap here, and this is a lower rank matrix. It's closer to low rank. When I add another layer, the effect becomes very, very potent. The small singular values, they just don't move at all, and you just get 5 large singular values corresponding to the fact that this is a rank 5 matrix that you're trying to complete. And this is actually much more accurate recovery. I'm not showing the figures here, but depth 2 is much better than depth 1, and depth 3 is much better than depth 2. Bottom line is that we see through trajectories again that depth does lead to a tendency towards low rank. It's not necessarily something that we can characterize with a norm or anything like that, but this dynamical analysis does reveal this. And this is the third example where trajectories allow us to go beyond the kind of tools that we are accustomed to. So let's conclude. So the perspective that I'm trying to convey here is that understanding optimization, generalization, deep learning through the language of classical learning theory is not necessarily possible. And it might be beneficial to look at the trajectories of gradient descent, look at the course of learning. We did this for linear neural nets. We showed by analyzing the trajectories that depth induces a preconditioner of a certain kind. And we used this to analyze optimization. We derived a guarantee of efficient convergence to global minimum, which to my knowledge is the most general guarantee of its kind. More surprisingly, we saw that depth could actually accelerate convergence, even though it gives you non-convexity, and even in settings where it doesn't give you anything in terms of expressiveness. And for generalization, we showed that depth enhances an implicit regularization towards low rank. And that gives you generalization for problems like matrix completion. And the trajectories are able to shed light on phenomena that simple norms sometimes have more difficulty of doing so. So at this point, I'll conclude. Thank you.
Okay, let's thank Nadav again.